All right, and we are recording, so I will hand over the presentation to Group 11 to share with us their PETRI Microbioreactor.
Okay. So, hello, welcome. Thank you all for joining our presentation. We are Group 11, consisting of members Danny, Cassie, Enrique, Garrett, Vanessa, Iker, and Andres. And here we're presenting to you PETRI, our complete microbioreactor. Okay, so in this presentation today, we'll first be going through our project's Hedgehog concept, and then we'll be providing a product overview, following this with more details of each subsystem that we split up our device into. We will then provide a cost analysis and then conclude with why we should build PETRI and then a summary. All right, so PETRI, as I said before, is the name of our device. It stands for the Precision Environmental Thermal Regulating Incubator. It's the all-in-one autonomous solution to cell culturing, specifically aimed in being the most user-friendly and versatile device available. So user-friendliness is one of our premier focuses, and this is embodied through the welcoming and easy-to-use interface front panel, which consists of a 7-inch touchscreen, LED status indicators, and an emergency stop button. But really what sets our design apart from the others is our novel modular toolhead system. So similar to a CNC machine, we have an electromagnetic moving toolhead, which is shown on the right, that is able to couple and swap between different compatible actuation and or measurement toolheads. And so depending on the customer needs, up to 3 different toolheads can be mounted within the device and swapped interchangeably to perform different culturing processes. And since they all follow the same compatible footprint, this enables users or the designers to come up with new designs of actuation or measurement toolheads to further expand upon PETRI's functionalities.
So our group's bioreactor PETRI is shown here sitting on a lab table next to a model of an average adult. Its overall dimensions are 43 inches wide, 28 inches deep, and 24 inches tall. It weighs around 141 pounds, making it easy to move around by 2 people and fit through standard lab doors. There on the front of the machine, we have our large access door for setting up experiments in our incubation chamber. To the right of that is our control interface, which we'll explain a little bit more later in the presentation. On the right side, there's a power connector rated for 15 amps with a included master power switch and a gas input manifold where external gas bottles will be connected to the machine that can be introduced into the environmental chamber. On the top of the machine is a vent for that incubation chamber that can be connected to either like a fume hood or an external mass spectrometer if greater control of the gas concentration is desired. So all machine panels provide protection for the interior components while their striking and attractive branding make the machine aesthetically pleasing and equally approachable in spaces ranging from high schools to industry labs. With the panels removed, you can see that our machine is essentially separated into 2 separate areas. On the right side is the electronics control module, which contains all the needed electronics for system actuation, monitoring, environmental control, and more. And then on the left side is the insulated incubation chamber where cell culturing actually happens. This area is both temperature and atmosphere regulated and has the capacity to hold 1 well plate or 1 tube at a time in accordance with the customer needs. So, as mentioned previously, the capstone of our design is our tool changing system. The top right render here shows the tool changer and plate shaker, which is contained in that insulated box that I showed on the slide before. Most machine functionality is implemented through our tool changing technology, including the fluid handling and ODFI measurement tools. At launch, there's going to be OD and FI tools for both well plates and conical tubes, as our method for collecting that data differs a little bit. And then we're going to have a single 20 milliliter syringe fluid handling tool for all the tubes and most of the well plates. And we also have a 4 syringe array tool for more parallel testing on the 384 well plates, just to increase those fill times. As mentioned before, the tool changer gives the user the ability to add more functionality going forward as their needs change. So the system is based on a kinematic coupling with an electromagnet. So a 3-dimensional motion system that has a similar design to consumer level CNC machines positions the tool changer behind the desired tool. It then moves forward so that the ball transfers, which you can kind of see right here, align with slots on the back of the tool plates. This forms a kinematic coupling that constrains the 6 degrees of freedom of the tool. And then finally, the electromagnet, which is rated for high temperature and the needed strength, is turned on, which pulls the steel plate into the coupling, securing the tool for use. Our system can hold up to 3 tools on this rack right here, and you can easily swap those out based on what the needs of the experiment are.
And so now we're going to transition into our subsystems that we separated our device into. This was to ensure that we met all of our 35 customer needs. And I'll turn it over to each of our other members to give a little bit more detail about these, along with some analysis associated with each. And again, here's a graphic depiction of how all of the needs were assigned to each of the 5 subsystems.
So looking into the fluid handling system, you see from earlier, we have 2 different tool heads that we have created for now. We have the option with 4 syringes or with 1 larger syringe. And each of these would be actuated using a NEMA 11 stepper motor with an M5 lead screw. And we use this lead screw because of the extreme precision that it allows for. And when it comes to cross-contamination, if you wanted to avoid that, you could put in multiple tools at a time, considering we had 3 slots open for tool heads. So you can put in, let's say, 2 different sets of fluid handling tool heads. One would be for fluid addition and one would be for subtraction. So it wouldn't come in contact with the previous, let's say, removal of liquid. And we have fluid waste and source containers that are underneath the tool heads that you saw earlier. And those are easily accessible. And lastly, the well plates are natively accommodated in our system. And then for the conical tubes, we have 3D printed adapters for either 15 or 50 ml tubes that those can be placed on to where the native tubes would be placed on. And then looking into the actual results that we can come up with, our precision, as you can see, is extremely high, going into 0.03 microliters. And that's, again, due to the using a lead screw on a stepper motor. And a stepper motor can get to about 200 steps per revolution. And then looking at the fluid dispensing rate, we can get just above 300 microliters per second, which is above the ideal. And on the last row of the table, you see motor force versus syringe pressure was looking at the amount of pressure that it takes in order to push the liquid out of each of these syringes. And it was about almost 1 kilopascal, and the stepper motor can produce about 75 kilopascals of pressure inside of the tube, which basically allows for, if you wanted future add-ons, you can create a tool head that had multiple syringes in it to be able to fill the plates quicker. And so there's a lot of clearance there in order to put multiple syringe heads, which would allow for, there's enough clearance in that regard. And then lastly, in the TRL level for this would be around 2, because we've done analytical studies, but we haven't actually prototyped this part.
So our next subsystem for PETRI is the machine enclosure. And the machine enclosure consists of the main support structure, which houses all of the other subsystems and ultimately provides the user interface. And some of the key features of the machine enclosure, as stated before, are the dimensions are 43 by 28 by 24 inches. And this allows the entire device to fit through standard lab doors and also fits on a standard benchtop, which was a customer need. The frame is made out of 80-20 aluminum extrusion, and this was used because it provides great modularity with the T-slot fastening system, and it also allows for ease of assembly with just a hex screwdriver, which would facilitate any future design modifications if needed. And then on top of the frame are some painted aluminum sheet metal panels, and these they provide the overall aesthetic appeal of the machine, and they also conceal any unattractive wiring or electronics. And it also supports the actual user interface, so the touchscreen, the status indicator lights, and the emergency stop button. As stated before, with the fluid handling subsystem, the machine enclosure is also technology readiness level 2, because we haven't prototyped it or done any physical laboratory studies on it. And a few other features of the machine enclosure are the emergency shutoff system, which, as you can see in the picture, is actuated by a red stop button. And this would cut power to the motors, the heating elements, and also close the solenoid gas valves to prevent any, to completely stop the processes happening in the machine in case of an emergency. Also featured on the front panel are some status indicator lights, and these visibly indicate the status of the machine, so whether it's on or off, what processes are happening, and whether there's a system error. And this would allow the user to relay basic information or to receive basic information about the device at a quick glance without having to interact with the touchscreen. And then if they want, they can gain more details with the touchscreen. And then finally, the door on the front panel is an insulated, user-friendly design due to the push to close, push to open grab latch, which facilitates the handling of the door, so that they can just apply pressure to close it up and pull to open. They don't have any additional handling, and it reduces the hassle for the user. And the door is sealed with EPDM closed cell foam, which seals the entire chamber and prevents any gas from escaping.
The next subsystem that PETRI has to offer is the electronics and control subsystem. And this subsystem satisfies customer needs in various ways. It allows for system control, data collection, and user interaction through the two main components, which is the Raspberry Pi 4 controller and the Roomba motor controller. And the Raspberry Pi 4 controller is used because of its high cost to performance ratio. It has up to 8 gigabytes of RAM, and it has memory capabilities of up to 500 gigabytes of storage. And it also allows for gigabit networking. And the Roomba motor controller has 6 connectors for motors. It allows attachments for multiple temperature sensors, attachments for pulse modulation fans, attachments for end stops, and other auxiliary electronics. And the control system also comes with limit switches inside the incubation chamber, which will prevent damage to the machine if something goes wrong, and it could also prevent injury to any users. The electronics and control system provides an intuitive and programmable user interface, and this is done with the Raspberry Pi using the programming language C, which is a common programming language, and it runs on Linux operating system, which is another common operating system. And using both this common language and this common operating system would just lead to an enhanced user experience. And overall, the electronics and control system consists of low-cost components, but widely available components. Linux OS is a free open source operating system, and the controllers used are inexpensive yet effective. And this subsystem also allows for closed-loop control, and this is done inside the reaction chamber where environmental conditions are regulated through temperature sensors, heating elements, and fans. The technology readiness level is level 2 because we have not performed an analytical study and this has not been prototyped yet. And here is the tabulated power consumption. So our power supply has a maximum consumption and 500 watts available. Yet, as you can see, the total exceeds the 500 watts. And this is not too alarming since these are all maximum values, and not every single component is going to be running at maximum power during the process. But if this does bring a problem, there is space available to add another power supply due to our modular 80/20 frame.
The culture processing subsystem involves major components involved in cell culturing. One of these main components is the optical density and fluorescent intensity measuring tool. It performs readings using a combination of an LED, a focusing lens, a filter cube, and 2 photodiodes. Its main features are that it can perform individual well readings, is available in 2 configurations, one optimized for vertical readings through well plates and one for horizontal readings through conical tubes. And it is capable of achieving the required light intensity of 1 kilowatt per centimeter squared. Another major component of the system is a shaking mechanism, which is also the area where the plates and tubes are mounted in PETRI. It is capable of independent X and Y axis motion using a belt system and a lead screw. And this independent motion allows for linear, orbital, and double orbital shaking patterns, along with any other 2D patterns that the user might desire. In general, the culture processing system has fluid handling tools and feedstock reservoirs that are made of non-reactive and non-porous materials, specifically polypropylene, stainless steel, and glass, which makes them safe for cell culturing. So this system, like the others, has a technology readiness level of 2 because it was limited to analytical study. One of these analyses performed was an optical analysis on the ODFI tool to determine if that light intensity of 1 kilowatt per centimeter squared could be achieved realistically. So on the left, there's a diagram of the path of light through the different components. It goes from the LED through a focusing lens to the filter cube where it's reflected down towards the cultures. And using the optics equations shown on the bottom left and the component specifications shown on the right, we got the results that the distance from the lens to the filter cube needed to achieve that intensity is about 4.76 millimeters. And this distance is something that can be achieved taking into account the size of the components and the geometry of these components. And it's a distance that you don't need any special technology to make sure it's the correct distance. The second result is that the area of light incident on the culture at this intensity is about 0.84 millimeters squared. And this is a small area, but it's not too small to be useful, as you can still fit thousands of cells in this area, and it's a pretty good sample size.
So also regarding the culture processing subsystem, when designing the shaker mechanism, a concern that arose when designing it was the possibility of any effects from the deflection of the cantilevered lead screw that drives the actual well plate holder. So the concern was that maybe the downward deflection due to the weight of the holder could affect the precision of the tool exchanger. So to verify that this wasn't a major problem, we performed a mechanics and materials analysis and confirmed it with an FEA simulation in SolidWorks. And the results of these analyses were a maximum downward deflection in the worst case scenario, so at the very end of the lead screw, to be around 0.4 millimeters, and the FEA resulted in around 0.8 millimeters. So overall, this deflection of like less than a millimeter can be accounted for with a simple calibration of the tool exchanger, and would it be a major problem for its performance?
All right, and for our final subsystem, this is our environmental management subsystem. And as the name suggests, this subsystem is responsible for providing and regulating the environmental conditions that are within the incubation chamber. And so 2 of those conditions are the gas and temperature conditions. So for the gas conditions, we have provided the sequence of plumbing that's going to take place. So outside on the exterior of the machine, there are 5 intake valves. And this was specifically to accommodate for the customer need that they want to be able to inject and control hydrogen, carbon dioxide, oxygen, methane, and nitrogen all at once. So a user would hook up these external tanks to the intake valves, which then they'll be controlled by high pressure solenoids. Check valves are also in place to ensure redundancy. The gases will then be plumbed through a gas manifold, which then will go into a mass flow controller, into which they'll be dispensed into the inner chamber. An exhaust will be left from the incubation chamber through the sealing valve, where it then can be ejected into the laboratory's ventilation system, or as mentioned earlier, used with a mass spectrometer to enhance the closed control of the gas regulation. And so for the temperature control, we decided to go with a thermoelectric Peltier heating and cooling system. This was selected over any other kind of system because it's solid state, so it doesn't require any kind of fluids. It requires less parts, it's more compact, and although it's not as efficient as other kinds of cooling and heating systems, you can add more modules to increase the effectiveness. So that's what we did. We used 2 modules, which is shown in the bottom right corner within the incubation chamber. So one side of the module will be on the inside of the incubation chamber, while the other will be on the exterior. And each module consists of a 2x2 Peltier element array. There are also 2 optimally designed aluminum finned heatsink arrays, and then there are 2 12-volt DC mounted computer fans. And other features to the subsystem are polyurethane spray foam, and this is to maintain interior thermal conditions within the incubation chamber. And then also we have external side vents on the exterior of our machine just to reject any heat that's coming from the thermoelectric system. And so the analysis associated with this subsystem was dealing with the fin geometry that we selected for our heat sinks. So our system was modeled as a closed electronics box that's shown on the left-hand side, since there is some internal heat generation. And with this system, we wanted to enhance the cooling and heating capacity. So by doing this, we incorporated fins. And so to determine what the optimal geometry of these fins would be, we performed various simulations and looked at what the temperature range was for a given current variation. And so in doing so, one of the outputs of this simulation is provided, and shown in the red line is fin type 1, which is ultimately what we decided with as being the optimal fin parameters, which include the fin thickness, the spacing, the length, the width, all of those parameters. And so those parameters are directly shown on our model that's included. And because we performed this analysis and we don't have any experimental data just yet, this subsystem also receives a technology readiness level of 2.
So the total cost of the machine is estimated to be around $7,000. This figure is the sum of the OTS parts, raw material to make our own custom parts, manufacturing costs, and assembly labor costs. Looking at this price breakdown shows that the majority of the budget is dedicated to the OTS parts. This is significant as our high use of OTS parts has translated to a reduced manufacturing time, while also minimizing the number of challenges associated with a completely custom machine's increased complexity. This has the added benefit that if our product is ever brought to market, using a majority of OTS parts opens up the availability to purchase these components in bulk to save money and increase the profit of selling the machine.
Lastly, we'd want to emphasize some reasons why PETRI should be built and prototyped. We believe that PETRI is the best candidate for performing the specified customer needs. It either meets them or excels at them. PETRI was developed with DFM principles in mind. As Garrett said, we ordered mostly off-the-shelf components to minimize manufacturing time. which allows Petri to be prototyped very quickly, which will lead to an operational machine. Prototyping Petri will lead to performance validation. By doing this, we can gain user feedback, which can allow improvement on the design of the machine that may have been overlooked since it hasn't been prototyped to raise its technology readiness level. And we can address potential points for improvement for further iterations. In short, Petri allows for future expansion of cell culturing capabilities through the modular toolhead system. Since we don't know what the future of cell culturing measurements will require, we designed Petri with expandability and future-proofing in mind. The system can perform all the required customer needs now, and the operator or researchers can modify the existing toolhead templates to add additional functionality to the machine. Since Petri combines several existing cell culturing technologies into one easy-to-use machine, there are several benefits that arise from this. The compact size footprint allows multiple devices to coexist in a limited lab space. Where 3 devices may have taken up a lot of space, now they're contained in one, and more devices can be brought into the lab, which may have a limited lab space. It also reduces the amount of training and machines that a lab technician or a researcher would need to use and learn daily. The autonomous operation of Petri has a lot of benefits as well. Since it can be remotely controlled, this eliminates the need for a operator to be present at all times during the machine operation once it has been set up. And since there's software and hardware safety features inside the machine, this allows Petri to be left reliably unsupervised while it's operating, which is safer than needing to have someone on site at all times. Finally, we'd like to extend a thank you to our sponsors and everyone who joined this meeting. We're looking forward to answering all and any questions that you guys may have. The floor is now yours.
All right. Thank you for the presentation. Very good job. Do we have questions from our panel?
I have
Tom, do you want to, or Jim, go for it.
Okay, yeah. I have a question about the culture processing module. What is the method you use to measure optical density and fluorescence intensity? Can you tell me more about the details?
Yeah, sure. So they're using light of a certain wavelength and intensity. It shines through the cultures. So for the optical density, it's measuring how much intensity is lost as the light goes through the culture from what's being emitted towards the culture. And for the fluorescent intensity, it's a similar measurement of light intensity, but it has to do with the light being emitted by the cultures in response to the light that's being put onto it.
Oh, yeah. What I'm asking, what is the device doing in measuring? I know optical density and fluorescence intensity.
Right. Sorry.
How this
Yes.
is going to measure it?
So for perspective on this, Dr. Penn is one of the customers. He's one of the representatives from the customer group. So he's actually going to be using this, which is why he's asking that question.
So it's being
that swings out, and then the shaker positions it underneath so that the light travels from the plate through the weld plate down to the photodiode.
Okay, and then
and there's sorry.
Please go ahead.
For the individual wells, there's a movement system that holds the tool. So, and that translates it from well to well, both in the X and Y direction, so you can get each individual well reading.
Okay, so for the OD, you are measuring at the different side of this well. And then for fluorescence, it's at the one side. Is that what you're doing?
Mm-hmm.
And you are using LED as the light source.
Yes.
And the LED is sitting below this plate or above this plate?
So yeah, if you can see the mouse, right?
Yeah, yeah.
Yeah, so the LED is there.
Mhm.
And it goes through the filter cube, and the filter cube, it has a dichroic mirror inside of it that reflects it at 45 degrees down to the cultures
And then the photodiode is beneath that?
above. That one's for fluorescent intensity because the dichroic mirror also filters for what wavelength they're looking for.
Okay. So there's certain range of fluorescence you can measure, right?
Right.
Okay, and you're using a photodiode to do that.
Yes.
I think I'm worried there might be issue with the sensitivity of using photodiode and in this this
Yeah.
setting because you are losing lots of photons in this kind of setup. But there are methods to address this. But you mentioned, I remember you mentioned you can divert this out of this device to use an external spectrometer to measure it. Is that the case?
That was more to do with the gases
Okay.
in the system. About the sensitivity, that is the reason we selected filter cubes specifically because they have a higher transmissivity overall, so there's less loss of light. And the photodiodes selected were at a higher sensitivity for the wavelengths that are probably going to be detected. I think. So.
Yeah, there's more detailed calculations you can do on this, and yeah, but I mean, I sorry, I don't want to take up too much of time for
Oh no, you're fine. If you want to give me your email and I can give you more like specifics on the actual.
Search my name. I'm a MAE faculty. You can find my email there. But the other question is about the environmental module. What is the, have you calculated the fluctuations or variations? So fluctuation is over time, like what do you expect? It will change, and the variation is like spatial change inside this incubator, because these are the two parameters. When you go buy these incubators, they typically tell you what are the variations, what are the fluctuations. And the other thing is what ambient temperature you can use this, because the temperature you can achieve inside is also coupled to the ambient temperature you're using this in, right? Do you have this kind of data?
Since we weren't given exact specifications on flux or anything, just a temperature range, that was our major consideration. So we haven't done any further computation with flux.
Okay. So so you treat it as a sort of a specified volume, and then you have a heating element, and then you use the mechanical sort of circulation to simulate that you can achieve this 4 to 70 Celsius, and then that is how you claim how it is meeting this customer needs, right? Am I correct?
Mm-hmm.
Okay. Okay. Yeah. Thank you for this. I'll leave it to other panelists to ask questions.
Guys, I'll touch on this because I know if I don't, Dr. Nemi will, and I'll be nicer about it. You mentioned that the weight of your box is 141 pounds.
Yes, that's correct.
And you said that's easy to lift with two people?
That is what I claimed.
Which two people?
That's a good question.
Okay. All right. So so that said, your shaker, you had a what appears to be a big old cantilever out there, right?
Yes.
And you are looking at, I guess, the weight of the tray and the support piece, and you're claiming that you have a deflection, on the order of 0.5 millimeter or so. Did you consider the linear actuation and the transverse motion of the system? Because I mean, just in general, big old cantilevers are kind of scary. They have low natural frequencies. This doesn't seem like a system that I would want to shake something on.
Unfortunately, we did not. I apologize. we mostly thought since the shaker plate is less, I think it's like around, like with the topper and everything, the most we would see was like around 137 grams, which was like less than a Newton per beam. So we didn't actually do an analysis on like the frequency during the shaking. So that's something that we'll take into consideration for the final design review.
Yeah, I think I'd be much more comfortable with that if it were supported in some way on the other end.
Okay.
I
Appreciate
told
the
you
feedback.
so. I did a design review with these guys like 2 weeks ago. They asked me to come and roast them, and that was the first thing that I brought up when I saw their design.
Yeah.
So, and I told them that somebody else would bring it up during their final design report. So thank you, Tom.
No problem. Happy to help. The other thing, because I'm kind of hitting on structures stuff because that's kind of my jam. Your fluid dispensing system, right? Can you flip back to that slide? All right, so it looks like you've got a lead screw that's set back from the pipettes by I don't really have a good sense of scale on here, by maybe a centimeter or so.
Yeah, it's around there.
Yeah, and then you're claiming that you've got an accuracy on the order of microliters of fluid, or fractions of a microliter of fluid. Is that right?
Yes.
Is that based on just the step size of the motor?
It's the step size with the actual linear distance per revolution of the lead screw.
So have you considered compliance of your system for this? Because having an offset like that is going to want to bend things, and you're not going to get, you're going to get a little bit of flex before you start dispensing fluid, which is going to impact your accuracy.
Yeah, that's a good point. These are all things we could definitely reach out to you if you're looking into. We can email you following up on that regard.
Easy fix is to put that lead screw in line with the syringes.
That'll be much more effective.
So, because right now, if you think about it, you've got something here, and it's being driven on one end, and it's got something that's pressing down on, so it's going to want to do this when it starts off. But if you put them in line with one another, it can't happen.
Okay, that's a good idea.
So one thing, if you go forward, I think it was, or to the picture of your motor with the, so 80/20, perfect. We'll start there. I think I talked to you guys about it before. So we discussed the 80/20 and everything like that. But how stiff is your frame?
I cannot tell you.
Yeah,
Stiff
okay.
enough.
I'm just saying, like, when you have a door that's being opened up, you have things moving around inside of it. 80/20, how many of you guys remember DML? And you like pick your robot up and twist it to get everything to line up correctly, and you set it back down for your second run. It's like 5 minutes of rattling around, and it's all the fasteners are already loose. You've got to be very wary with that with 80/20. Like, my concern with things shaking around inside of it, your frame's just going to loosen up, and you're going to end up having a parallelogram instead of a box.
Okay.
So it's just yet another concern with 80/20. I'm not going to beat a dead horse, though.
Okay. I appreciate the feedback on that. Definitely look into that.
I have one last question. Do you have a rough estimate about the throughput of the system? For example, when I'm culturing cells, can I use 3 of the plates together, or there's only 1 plate I can use?
So the customer needs statement that we went around said 1 well plate or 1 tube per environmental system. So that's what we designed for. But if you look at you can pull it up, like the conical tube right here, you could potentially fit more than 1 of those in, just because you just need to space out that plate, which they would have the same environment, but you could still have 2 different tests going simultaneously. But yeah, well plates, you're constrained by the shaker capacity of just one.
Okay, so the system is designed with one plate sitting inside the entire framework and then moving around and then doing measurement. Okay.
Okay. Any other questions from?
Is the tool changer latching system, is that an OTS part, or are you guys custom making the parts for it?
It would be custom made. Like the plates would be water. I mean, like the ball transfers here, those are an OTS part. The magnet's an OTS. The actual plate here, that's just like a milled part, and then the plates that it made up to would just be either milled or CNC'd.
Okay. What do you guys expect your repeatability to be? Like, do you guys have any worried that it might drift the repeatability of being able to pick up the same tool over and over again and the needle be in the same exact place? Or
the system that we took inspiration from for designing this system, which operated the securing method was slightly different, but the coupling was the same. They were seeing repeatability, I believe, somewhere at like the 1/10 of a millimeter or so, which for the size of a well plate, like you don't need to necessarily be in the exact center based on their shape. You just need to be like within the however many millimeters wide, which for like a 384 well plate, I believe they're like 3 millimeters wide or so. So it should be good enough for what we're trying to accomplish here.
okay. And then my last question about the tool changer is, how are you guys handling the cable management of pulling off the tool head, and then how do you handle the wires attached to each motors on each of the different tool heads?
Yeah, so that was still up for discussion as to what would be the easiest to implement, but the plan was to put connectors on each of the tools to where there were just like the actual connectors up for debate if it's like a PoE or like USB that's locking, and you would just connect the cable, which would be like up above, down into the plate that you're using whenever you set up the machine. And then based on the range, the cable would just kind of, since it's secured at the top, have enough room to move around, if that makes sense.
Yeah.
For a second, I was really scared that you said you were going to have a connector over on
the tool changer.
On the tool changer?
Oh, no, there's not on the tool changer.
I was just like, oh my God, you're never going to get that to connect. Like,
no.
The first time you try and do that with a USB, you're going to have a bent USB. It's going to be terrible.
Yeah, no, all the connections would be on the actual plate.
Yeah, so it'd be on the, okay. And you'd be like, all right, cool, I'm doing optical density stuff. You just connect up the optical density tool and your, for lack of a better word, pipetting tool.
Yeah, you would just do that, and then within the software, you would specify like, okay, I want to do this, like say this tool's in position 1, this tool's position 2, and then it would know, okay, I need to output a motor command here or that kind of thing.
Very cool. Good job, guys.
Thank you.
All right. So we're actually a couple minutes over at the end of time. So let's wrap it up there. Let me stop recording.